In another demonstration, I've shown that running a current through these coils of wire, these loops of wire, which surround this iron bolt, create a pretty strong magnetic field. A magnetic field capable of, say, attracting one of these balls from a short distance. Well, I want to demonstrate something here, and this just occurred to me because I'm doing this just after demonstrating what happens when I, well, you don't see the coils, the Helmholtz coils. These things, when I change the magnetic field within the coils, well, you can't really see them. So we'll put that aside, but hopefully if you've seen that, you understand, I think, what's going on. I'm going to repeat that with these coils. Now, there are probably fewer loops in these coils here than there were in the Helmholtz coils. But I have this iron core, and now I'm going to change the magnetic field. Well, you can see right there, just by moving this closer and further, and maybe pulling it away really fast. It's pretty, or letting it, okay, or just rotating it as I did with the Helmholtz coils. We see that we get a pretty good response, at least as good as what we got with the Helmholtz coils. And what's going on there is, without talking about magnetic domains and so forth, there's essentially an alignment of, well, the magnet in the presence of this iron core tends to align magnetic fields of the atoms, actually magnetic fields of collections of atoms within the iron. And every atom does have a magnetic field, as we'll see, because every atom is essentially a nucleus surrounded by electrons that move around it, although that's not really what they do. So I don't want to go into an explanation of that, but the movement of electrons or the quantum mechanical effects of the electrons within the atom make every atom magnetic. In most materials, the little magnets created by the atoms are in random directions. Okay, and that's also the case pretty much with this iron until I bring a magnet close, and then the magnetic field of this magnet causes an alignment of the magnetic fields within the material, which enhances the magnetic field much more than it would be if I didn't have the iron core in there. So I have a much bigger magnetic field within these coils than I would if I just had air. Now that leads me to another thing. I've never done that. I've never tested that. Pretty obvious, but you don't think of everything. Okay, so here I've got a bunch of iron. It's actually in the form of steel, okay, within the Helmholtz coils. So I'm going to hook up the galvanometer. And again, I've never done this before. I just looked around and saw what I had that I might insert within the coils to give me a magnetic field that I could enhance. And let's just see what happens. Not that extreme, but it's more than what we had earlier. If I get the magnet closer, we get a stronger field within the steel balls. If I had a 20 centimeter or 19 centimeter core of iron that I could put in here, and I wouldn't want to do that because I'd probably end up damaging the coils, I would expect to get pretty substantial response from these coils. Okay.